Hello, everyone. Welcome to room 2. We're about to hear from Adam Phillipps on the intro to item similarity and the embeddings that make it work. If you have questions, please ask them in the box next to the video or in Slack room 2. I'm going to hand it over to Adam to run us through the presentation. Thank you for joining.
Hey, everybody. Just got to share my screen real fast. By now, I wish I was better. Or do I need the view? There we go. Sorry. I just had this figured out and then forgot. Okay. Let me know if you can't hear anything. And I'll try and get to your questions, but I guess there's a delay, so we'll figure it out as we go. But my name's Adam Phillipps. I'm a machine learning engineer at Overstock, and come to you today on this fine Thursday to talk about item similarity and some of the techniques that we have to make those things happen. Not really going to try and do any real math. There's very little math squiggles in this talk, and really what I'm shooting for is just to give you guys an intuition about how all this stuff works. So kind of like you don't need physics to be able to ride a teeter-totter. Just kind of understand how that thing works. So item similarity. It's a pretty simple concept. We do this all the time. Like, you know, if I give you a song, you can give me 10 songs that are really similar to it. Or maybe you give me a picture of a car and I can name off a few cars that are a lot like it. So we do this all the time, and like it's all over. There's a broad array of things that use this in our normal lives. You know, the medical field can use this technique for finding cancer or genetic defects in their treatments based on other similar successful approaches. And in the education space, we can try and find similarities in how students are behaving. And then, you know, if one looks like they're going to fail, we can head it off early. Or in the retail space, it's everywhere. Like think about Amazon. You go to buy something and they're always showing you similar items down there. So we use this stuff a lot. It's all over the place. And since the nature of data these days is so big, you know, we have so many things we want to look through on Amazon, and they're selling so many things. We need to use computers to get there. So that's really cool that computers can do this. But the downside is we kind of have to tell them how to solve the problem. And kind of as I see it, there's two approaches that we can take. One is a standard logical approach. We're probably all pretty familiar with this kind of thing. It's like if-else's. So let's just work through an example. Pretend I run a retail website and I have like millions of things that I try and sell. And I want my website to be able to take an image from you. Like you can give me an image of a thing, and then I will suggest you 10 things like it that you could buy from me. So if we try and do the logical approach like this, so I get your image and my code loads it, excuse me, and then my code says something like, okay, if the thing in this image is rectangular, and if it looks really thin, and if it's made out of fabric, and if it's got a pattern on it, well, maybe it's a rug. And so we could dive down further into our logic, you know, and say, if the pattern is kind of linear, and if it's sort of reddish in color, well, these could be similar. But you also got to build in some logic, like to differentiate between a rug and a bed sheet and a curtain and, you know, various things. And you throw in couches in the mix, and we have to differentiate, you know, what does rectangular mean on 3 dimensions, and so on and so forth. So doing it the logical approach gets ugly fast. Sure, you can imagine. You know, your code is huge. Got a bajillion if-else's. They run butt slow, super hard to maintain, really hard to update. There's got to be a better approach. So, algorithms to the rescue. I know of one algorithm that we can use that for item similarity that uses distance. So, like, how would you use distance to find similarity in a couch versus a lamp? Not so intuitive right off the bat, but it's pretty simple once we dive in. So let's take a little example about people. Say I want to find similar people. So I can sort of build a space that describes people. We'll just do a two-dimensional space, height and weight. And then we go ahead and measure distance between these guys. You can do the math to measure distance between them, but it's really easy to visualize in a graph like this, a scatter plot. So kind of how it boils down is like, if you take a look at this graph, up and to the right, we got heavier, taller folks, and they're probably kids because nobody's even 6 feet tall here. And down in the bottom left, we probably have smaller, what appears to be helium-filled children, or maybe cartoon characters, I'm not sure. But we've got all our folks plotted on this graph. And if you look at the yellow circled individuals, you notice how they're really close together. The distance between those two is really small. So when we think about like item similarity and we use the distance algorithm, the closer something is, the more similar it is. So like, look at these two people here circled in red. They're not quite as close to each other. Their shape is a little different, you know, their size and height are off a little bit. So you can kind of see how this is breaking down. We can just use distance to see similarity. So this space might work really well for guessing somebody's jacket size, but in reality, it's a little more complex usually. Like, I'm not trying to figure out your jacket size. I'm trying to sell you a jacket. So what we've got here is a 2D and 3D graph. On the left is the 2D one that we already saw, and the right has the same exact data, and we'll go over it in a sec. And you can see in the 2D graph, our people, our yellow folks, one of them, Monopoly's uncle, is about the same size and shape as Manfred the hobo. So they're pretty similar in this space, but you know, when we think about like selling a jacket, that is not useful. This similarity score sucks. It doesn't help. So one thing we can do to kind of improve our similarity scoring and searching and stuff is to add in another point of data, another dimension. So yeah, on the 3D graph, we still have height and weight, and we still have everybody plotted in there like that, but we also thought about income. And you can see Moneybags is clear off in his own place. So we're gonna sell Moneybags a different jacket, like probably a really expensive one, nice one, and Manfred's looking for the best bargain. So you can see that like if you add in more meaningful dimensions, you can get a little bit better similarity score. That was tough. But it doesn't always work. Like, you can't just throw more dimensions in there and expect better results all the time. So like, same data here, same people, but this time instead of income, our third dimension is how much is this character a space alien? Most people are 0% space alien. So, you know, like we see Manfred and Moneybags, they're back together again, and our similarity score is pointless. Interestingly enough, we do have a few aliens in the mix, but they didn't factor in at all. So this kind of just shows you that throwing more dimensions into your data doesn't always help. They have to be meaningful. They have to be like, hold some sort of meaning to your data, to the thing that you're trying to find similarity for. So like when we sell jackets, income is helpful. It helps us figure out how a customer is similar to another. Space alien, ship, or ness, not so good. So, you know, that's all fine and dandy. We've got a good concept of, you know, I can use a distance to figure out similarity, and I got to make sure that my values have good meaning. But what do you do if it's kind of tough to figure out values for your data? Like, what about the song example we had earlier? What attributes would you compare to figure out, you know, is this rap song the same as this death metal song? Do they both have the same beats per minute? Not the same. You know, the pictures of the cars. How do you get values out of your data like that? And also like text. What if you have descriptions of stuff? Could you not also try and find similarities in the way things are described? It's not so easy because, you know, like with height and weight, those are already numbers and they already kind of have a meaning about your size. And so that kind of tabular data, we can just kind of readily use. But stuff like images songs, sounds, and text data takes a little bit more work, but it's super useful. So I figured we'd dive in on one of those. Let's take a look at some text and how we can try and get a meaningful space so we can get item similarity out of it. So I have 3 pieces of furniture here. They're just kind of ottomans, and they have descriptions to them. And if you read the descriptions, they have a little bit of nuance to them. You know, sort of like I would describe an antique Model T car differently than I would describe a new Ferrari Speedster. I'm going to use different words and stuff. So our descriptions are also doing that. And what you might notice is the first 2 sound a little more the same than the next. That cool orange one. So basically what we got to do here is figure out a way to get these descriptions. We can send them through a process, and then we need meaningful numbers to come out of the process, you know, so we can do the item similarity scoring. So at a high view, that's kind of what we're doing. In our example, you know, we're a retail store and we want to get meaningful list of numbers out of descriptions of furniture. So we take all of our descriptions, they're just called documents. Take all your documents and you send them through some magical hand wavy process, and bam, out comes semantic vectors. So what is a semantic vector? That's just the meaningful list of numbers. You know how like in our people example, we were looking at 3 dimensions like height, weight, and income. So those would be like the columns for your different data. And then each row, each human being in your little Excel spreadsheet, those are vectors. So a vector is like a description of one item, and it's got dimensions. Semantics means it's got good meaning. So that's what we're trying to do. Send documents through some magic and then have semantic vectors. This is kind of like an exploded view. Same deal though. We've got our descriptions, and the pictures are just for us. Like, we're not going to send them through the magic, but they're for us to see so we can compare. So you take a description, you send it through the question mark magic box, and out comes a vector, that row in the little table there. And supposedly this thing is meaningful, it's semantic. You look at the next one, it comes out as another vector, and the third one too. So let's like look at these vectors. Let's look at this little space that we've got. It looks like 4 dimensions. I don't know what they are yet. We'll talk about that in a sec. So if you look at this first column, for each of the 3 vectors, we got 2.3, 2.2, and -0.3. All right, well, 2.2 and 2.3, they're right next door neighbors on the number line. A little further away than -0.3, but you know, you get the idea. 2.2 and 2.3 right there. Next column over, next dimension that we're talking about, where we got -1.1, -1.1, and -2.1. Well, same pattern emerges. Like the top 2 pieces of furniture, which look a lot alike and their descriptions read a lot alike, they've got really similar values here. And the next one down, which is a bit different, has a different value. So that's kind of like the concept in a nutshell. If we can describe our items with these vectors and like the numbers, when they're similar, the numbers are close, we've nailed it. So that's kind of like what we're doing in a nutshell. And this space over here is the magic bit that we need to figure out. We have to turn our words into numbers, and those numbers, they better mean something. We can't just throw random stuff like, how much a space alien is this piece of furniture? Wouldn't help. So that brings us to the meat. Embeddings are super cool, I think, and there's kind of 2 parts to them. There's the part that's really sort of easy to grok, to pick up and understand, and that's where we gotta, you know, take our text descriptions and put them into lists of numbers.
Hey, Adam, sorry to interrupt. We have a question on the prior slide.
Yeah, sorry, I kept going too far. What do we got?
That's okay. Question comes in from Fitz Bushnell. Is this really the only information provided to the magic question marks? The second description includes that it's an ottoman, but the others don't. That seems like it would be more meaningful.
Yeah, no, that's a great point. You don't get to pick what your description is. So this is all that we're going to feed it. we have to kind of massage that description a little bit to get to where we can spit out these numbers, and I'll go into that. But yeah, this would be all you get is the description. So we're going to build a meaningful vector out of each description. And that's it. So I hope that answered the question. We got a little bit of a lag, so feel free to ask again if I didn't clear it up there. But yeah, that's all we're working with here. And we're going to build an embedding about it. I mean, maybe I can go back to this slide and talk about embedding a little bit. These vectors that we have, you know, our values and the dimensions that describe them, that's an embedding, essentially. So that's the top part of the iceberg. We got to get our descriptions and put them into numbers. And the real important bit of the iceberg, the stuff under the water that sinks the Titanic, is the semantics, just kind of like what you were talking about, how we leave out the word ottoman. How is it supposed to know? Well, we have to build, you know, our magic process, the question box, has to be able to map the feeling of ottoman into our numbers. So that's kind of the devil in the details. Embeddings are not just a list of numbers that describe your stuff. They're also meaningful. Same adage, you know, garbage in, garbage out. If you build a crappy embedding, like up earlier when we were doing space alien as one of our dimensions, not a good embedding for figuring out similarity in customers. So you build a crappy embedding, you're going to get crappy similarity scores. They won't be helpful. So that's what we're going for.
And Adam, one more question on the prior slide. Sorry about that. For the columns, can you just run through what each of those represent?
Oh, biscuits. I left that out. I'm sorry, guys. All right. All right. So I wish I could rewind time, but here we are. Okay, so we see that the numbers are similar, right? Like when a piece of furniture is similar, it shows the dimensions kind of similar. And what is this first column showing me here? I don't know. We don't know, actually. It could be like the blue round fuzziness of the item. And the next one over, where we've got -1, 1, -1, 1, and -2, 1, that might be the degree to which this item resembles a bullet-ridden car. It doesn't, like, in reality, our magic hand-wavy process, it's not a human. It's not going to be describing things in the same ways that we think about stuff. Like, you know, with furniture, I might think, well, is it leather or fabric? That's not the same sort of pattern that emerges to our magic hand-wavy. But we'll go into it a little deeper. But the point is that the dimensions they're not really super easy for us to reason about. It's just something that our magic found a pattern in our data for. So like with the humans, we had a lot of vectors, you know, like 7 billion vectors for humans of height, weight, and income. And our magic hand-wavy process found some pattern in there. Maybe it's like, oh, these guys all live on the East Coast, and we don't know. It found a pattern. So that's what these dimensions are. They're just something that our process found a pattern in. Hopefully I didn't ramble on too long, and I hope I covered what you're asking.
Yeah, no, and Adam, I think one follow-up to that, which is a good segue. What are some of the models you use to get your semantic vectors?
We'll get into that. I would love to answer that right now, but there's a pile of crap in this talk, and I got to try and manage my time. So we'll get into it pretty soon, actually. We're right there. Excuse me again. Okay, embeddings. Right, embeddings are just the space that we're going to describe our items in. We create the space, and it better be meaningful space. So that's kind of the big important bit of embedding. So yeah, our mission. So remember, we're working with text data, you know, because I run a retail website and we have lots of descriptions of furniture. So our first objective in our mission is to turn words into numbers. Okay. And that's so we can do math with them, because you can't the plus cat. That doesn't work in math. So we have to turn our words into numbers, and those numbers better be meaningful. They better be semantic vectors. So let's focus on the first thing. We're going to turn our words into number, and this isn't going to be the final approach, but we need this step So like when we turn words into numbers here, it's not going to be perfect, but it's going to be something that we need, and it will help us kind of dive a little deeper into the thinking of NLP. So natural language processing. So it's a one-hot encoding. It's a way to turn words into numbers. There's lots of ways to do it, but we'll look at one hot. So building a one-hot encoding is pretty easy, and we can just do another example where, like, I want to build a one-hot encoding for all the words in a book. So I get a book, and I'm going to make a list of unique words. So like I'll start at page 1, and the first word I see is definitely unique because I haven't even started the book yet. So I put my word in the list. It lives at address space number 1 in my unique word list. So I move on to the next word. It's probably also unique because we're on the second word. So I throw that sucker into the list too, and it lives at address space number 2. So, you know, pretend we've got like 1 million unique words in this book. So we're going to eventually build a list of 1 million unique words. And that last word, it lives at address space number 1 million. So that's kind of like how the address space for a one-hot encoding works. And then when you want to build a one-hot encoding for a word in your book, all you do is you get a ginormous list of zeros. There's a 0 for every word in every unique word in our book, except there's a 1, a single 1 in one space. So for whatever word you want to represent, you find its address in the unique word list, and then you put a 1 there in your one-hot encoding word. So like, let's run through the process of building it. You know, we've got our second word in there, and we're all the way up to the 1,000th word. And we're going to go ahead and throw that into our unique words list, because somehow in this book, they've gone through 1,000 words without saying the. English is fun, huh? And so we take that word and we throw it into our list, and the lives at the address of 1,000, the 1,000th index. We do the same thing with cat. Cat goes in at the 1,001th index. Eats 1,002. So if I want to represent the word the as a one-hot encoded number list, lists are okay too, we just need numbers. So if I want to represent these as numbers, I take the word the, I find its address in my unique word list, it's at 1,000. So I've got 999 zeros, and then a 1 for the word the. And then a grip of zeros afterwards, you know, to equal all of the unique words in our list. So like eats. Eats was at the 1,002 spot. Same thing, got 1,001 zeros in front of it, and then a 1, and then a bajillion zeros after it. So that's a one-hot encoding. Hopefully you can kind of see how we build, you know, like you can represent any word in our book as a one-hot encoded list. So cool. We achieved our first objective. We built a way to get words into numbers. Huzzah, except, oh crap, those numbers are not meaningful. If you do the math on those numbers, like this distance scoring that we're all talking about, if you do the Euclidean distance between any one of those one-hot encoded words, they're all the same. The word the is the same distance from serial killer to at. Every word is the same distance apart. So we really lose a lot of meaning when we choose the one-hot encoded route. But we did get our words into numbers. So we got to find another way to carry meaning, you know, the semantics from our data into the semantic vectors. And before I jump into the next slide, do we have more questions?
No, nothing yet.
Nothing yet. Okay. Sometimes one-hot encoding is a little cumbersome for the first time. So if somebody pops one, let me know. Okay, so we want to find semantics. We want to build meaning into our semantic vectors, and the one-hot encoded did not do it. So another thing we can try and do is word2vec. We're going to take all our documents and vectorize them. This is the really high view. We take our documents, they go through the hand process, out comes semantic vectors. Oh. Sorry, that was the summary. We already went through the other slide. Yeah. Here is the way that we'll do it. This is called a skipgram. We're going to do it with a neural net. Spoiler alert. And, well, I didn't mean to click there. Earlier on, when somebody asked about the models we use, this is one of the models that we can use to build our semantic vectors. And we need the one hot encoded to make it happen. So here's the real high view of a skipgram. What I want to do is take a word and predict all the words around it. We're going to like use a little window, so this is reasonable. We'll have a window size on either side. We're only going to look at 2 words, okay? So like in this example, when I'm examining eats, when I want to send it through the neural net and have the neural net predict the cat tasty food. So I send the one hot encoded through the neural net and I try and predict the words around it. Why would you do that? Well, it's kind of cool actually. If you think about it, the words that we use in our sentences and paragraphs and things like that, they all kind of have a combined meaning. They all sort of go together. You know, when you're describing the Model T car, you use a certain kind of word verbiage to get to your description. When you talk about a really nice couch, use a different verbiage. So we're relying on that artifact of language where you can sort of get meaning and pack it into a word. Like the word eats, meaningful words around it are tasty and food. And in this case, the cat, because the book we're looking at is probably talking about cats and food or something. So that's the whole goal here, is we want to send in a word, predict the words around it, because language just kind of builds in nuance into our sentences and things like that. So how could this all work? Like, how can we predict words around it so that we can get semantic vectors, so that we can do similarity searching? We kind of need to take a little deeper dive into the neural net. And I hope you guys brought some Snickers or like some coffee or something, because it gets a little thick. You've already noticed, I guess. A little bit dense here, but we'll get through it. All right. So neural net. This is, you know, I'm sure all you guys have seen this, or most of you, just a basic diagram of neural net. And what we've got, all these little circles are called neurons. And the green ones, they're input neurons. That's where you send in your data. Like we'll send in our words into the input. And then each neuron is going to send its information to every neuron in the next layer. So these orange ones, they're hidden layers. So that top neuron, the top green one, top left, it sends its 0 to every single neuron in the next layer. And then they do some stuff and they send their info to the next layer and they do some stuff. So something that's kind of important to notice here is that this is a fully connected graph. We've got each neuron sending its info to each neuron in the next layer. And then they kind of wash, rinse, repeat, sends it to the next layer. So these orange ones, the hidden layer, they're kind of special. They do a little bit of work. They run a math function on your inputs. So like you send in this 0, the top neuron for input, you send in that 0, and all the hidden layer neurons in that first layer, they get the 0. And they're going to do a math function, and like good math functions do, they'll spit out a number. And if that number is above a threshold, then the neuron will send its info to the next layer. Like maybe our threshold is 0.5. So when the math function runs and it spits out a 0.6, oh, it met the threshold. We can send it on to the next layer. So that neuron would send its info to all of the neurons in the next layer. If it came up with an answer like 0.3, something below our threshold, it just lays dormant that round. So we do this for every word, you know, the cat eats tasty food and all the other words in our book. And we send them through one at a time. And hopefully on the other end of each pass, like each word that goes through, we can predict the words around it. The cat, tasty food. So I don't know, how does this help us and how does this happen? I think deserves a little bit deeper of a dive. At least it does for me. So I wanted to take you guys into a neuron a little bit harder. This is just like an exploded view of one of the hidden layer neurons. And all the X's on the left, X1, X2, those are inputs. So like that's where we're sending in our one hot encoded word. So like zeros and ones come in. And then they get multiplied by these weights. This weight 1, weight 2, they get multiplied. And then all of the multiplied inputs, they get summed up, they get added together and sent into the math function. And whatever that math function spits out, greater than or less than our threshold, it'll send it to the next layer or not. Okay, the important bit here, this is why I dragged you through all that, is the weights. The weights are specific to the layer before it, to the neuron before it. Like all those neurons in the preceding layer, they all get their own special weight to multiply by. So that's the important bit, because we're going to go ahead and adjust these weights later on and fine tune our predictions. All right, so probably a better way to visualize the forward pass in a neural net is to look at some animation that somebody else created. This one is a neural net that tries to predict the number that you've written. And you can see like you have to turn that picture of a 7 into a bunch of numbers so it can go in the input layer. And then it goes to the next layer, which is a hidden layer that runs those math functions. And some of them fire their information to the next hidden layer. Some don't, they just go to sleep. And in the end, eventually, we're hopefully hitting what we're trying to predict. So that's just like a nice way to see, to visualize how the neural net's working to move forward, to predict things. And that's half the battle in training. So actually, before we jump into error and stuff like that, are there any questions on what we're doing so far with Skipgram or the high view of the neurons?
Nothing on Slido, Atom, nor Slack yet.
Wow, you guys are rock stars. I would have been scratching my head. Maybe it's all the coffee you're drinking. So good.
I think you might have prompted some after this, so.
Okay, should I hang around or just continue?
Let's continue.
All right, sounds good. Excuse me. Okay, so how would that do anything for us? And what if like in our forward passes, we're just predicting really badly? How are we supposed to get better or train? That was the biggest part for me. When I was trying to learn neural nets, I couldn't understand anything beyond what we've already talked about. I didn't know how it got better at predicting. So we have to talk about error to figure out like how we went wrong. So we're going to try and predict. When we train, we'll try and predict, but then we're going to get it wrong. So we got to figure out where did we go wrong and then fix that problem. So we need to figure out a way to break this black box of a neural net down into pieces that we can examine or work with. Because right now, kind of how it's working is like you send in your one hot encoded word and magicals, and then out comes predictions. You're like, okay, they were wrong, why? So what we have to do is, instead of that black box, we want to break it down into each function that ran, that contributed to that prediction, that bad prediction. So what we got to do, yeah, these are the only math squiggles, I promise. And it's not even real math. Don't worry about the real math. What I'm trying to show you though is that we have tools to do it. Like one of the techniques, we're going to use gradient descent. It's calculus stuff. If you want to talk about it more in depth later, come hit me up or Google it. Chain rule and derivatives and gradient descent will get you there. But in a nutshell, here's what we're going for. So we have an error function, and basically that's our black box, like that was the neural net, except for backwards. We got to figure out, hey, how do we screw this crap up? We've got a black box to go backwards with. So we want to break it apart into its constituent functions that ran. Like each one of those neurons was a function that ran. So we've got a big map of functions that ran. And we can break it down into composite functions and build a computation graph out of this bad bear. And kind of what that works like is, so we've got like error of x. We've all heard the term f of x. That's our equation. So when we break it down into composite functions, it's going to sound more like f of g of h of x. You know, the output of one function is the input to the next, and so on and so forth. So we just break apart that composite function into its constituent pieces, and then we try and understand the error rate about it. And we can adjust those weights. I should have put this slide back in there. We can adjust those weights after we figure out, hey, it was neuron B7 that was to blame, and they were super negative. You know, we can adjust those weights is what we're shooting for. So this is kind of like an excerpt of the computation, the total computation graph. This was just one path that data could have taken through my neural net. We had the input, and it hit this blue neuron and ran computation and spit out its stuff, hit the next layer, and we're looking at this neuron here. It did some stuff, and we came up with a crappy prediction. So this is like how it looks like when you break them down. We're thinking about each individual neuron along the path to that bad prediction. And when we look at the error rate, we can see, oh, look, we had a very, okay, so for this first one, it says we had a positive error rate. So we just want to adjust our weights down a little bit so that we can try and zero out that error rate. We would just want to get a 0 error rate because that means perfect prediction. So we had a positive. Let's take our weight down a little bit for that input. From the blue neuron to the yellow neuron, the weight should go down a little. So we keep on going further in our computation graph over to this dark blue neuron. And we found that its error rate was quite negative. So we want to fix that. So we're going to adjust its weight from the input to this blue neuron. We adjust that weight to go up a lot because we need to try and zero out our error rate, you know, for perfect prediction. So that's kind of what we're doing. We did the forward pass. We tried a prediction. We sucked. We figured out who's to blame. And then we adjusted weights. And then we went to the next word. And we just keep doing this for all the words in our book. And by using that artifact of language where I'm predicting the words around it because they have meaning that's tied to the word I'm working with, we can try and get out good semantics. But how would that help us at all? This is a fun part of neural nets. You can train your neural net to predict words around a word, and then you can just not even care about your predictions anymore. You just lop off that last layer in the neural net because we don't care about the words around it. We're only interested in a vector, a semantic vector. But a vector, just a list of numbers. Well, as these numbers, as my data goes through the neural net, we're doing math functions, so it's numbers. And those inputs are being multiplied by weights. So now these numbers are, you know, less random and more meaningful. And so now that we've lopped off the last layer and we don't care about our predictions anymore, we can just consume the numbers that come out of the last hidden layer. And those are our vectors. So that was the super hardest part of our stuff. If you made it through and you're still awake, I commend you. And cool. There's no more crazy stuff left. We're through all this hard stuff. So I'll take a moment to pause for questions because there probably is some. Okay, we might be questionless.
Nothing yet, Adam.
Cool. Okay, cool. Well, good job. We made it through tough stuff. Feel free to enjoy the rest of your snacks. But now we're just going to kind of talk a little bit more from an engineering aspect. It helps me to understand things this way. Like I can get the intuition for item similarity, but how do you build a system to do these things, you know? So one of the steps that we have to do is to prep our data. It's pretty simple for text data. And the steps that I've written down here, they're not in any particular order. I just figured they're easier to talk about like this. So one thing that we have to do is to tokenize all of our data. So we take all of our descriptions, like this oversized floral patterns in bold tones is a description of something. And then we have to break it down into little pieces that we can process, little atomic type of pieces. So we just split it. We just split all the words out. Now we have a list of words. We've tokenized our document. Cool. Next thing we need to do is to put these things on an even playing field. So think about it. If you've got a word at the front of a sentence, it's got a capital letter. So would you want to build semantic vectors, out of our words? Do we want two different vectors for oversized at the front of a sentence because it's capitalized versus oversized anywhere else in the sentence? I mean, I would say no, because oversized is oversized. So once we downcase all these letters, we make it so oversized is represented by one vector, not two vectors. And yeah. So noise reduction is probably the coolest part of this piece of the data prep, in my opinion. Noise reduction is interesting stuff. One thing that we're going to do when we try and do some noise reduction is to remove stop words. Well, I guess I should back up a little bit. The point of noise reduction is so that we are like, it's like trying to listen to a conversation in a noisy room. If you can get rid of some of the background noise that isn't meaningful, then it's easier for you to pick out what the other person's saying. So what we're going to do is try and throw out some of the words that don't give us much meaning. They may give us tiny marginal amount of freedom, or I mean, not freedom, meaning, but they don't really help a ton. So if we get rid of those, we have less data to process and we get stronger patterns. And stop words are things that they're really common words in language, like in, this, from, the. We'd get rid of all those words because they don't add a lot. So like if you think about this, in English, I'm sure in just about every other language, if you remove the word the from a sentence, you're still going to be able to figure out what the sentence is about. So it's kind of that concept, like if we take these words out, it doesn't destroy the meaning in the sentence, and humans are still able to pick out the pattern. As it turns out, so are computers, so is a neural net, and it actually does a better job because it's less noisy. So that's a quick overview of how we get to a good, clean piece of data that we can vectorize and then do similarity searches with. But let's take a look at like how this might play out in some systems and some code. So what I've got here is a representation. It's pretty high view and simplified, but it's a representation of what we were doing to pick out, like when you sent my website an image and I matched it and sent you back some similar things, or we'll say descriptions this time. So you typed in like super fancy rug. So I need to take your description and find similar rugs. So here's how I make it happen at a system level. We've kind of got two pieces of this system. One is the offline asynchronous training stuff. And that can happen like daily or monthly or however often you figure out that it works for this data. But it has nothing to do with what the customer is going to be feeling. So we've got this scheduled job, and we'll say it runs like every month. And we want to get an item similarity search service out of descriptions. So how this could play out is like my scheduled job starts up. It connects to the database and gets all the descriptions for all of my furnitures and all the documents, right? And so we can go ahead and start processing this by creating n-grams. N-grams are like, remember when we're talking about Skipgram? And I said, we're only going to look at these two words around cat. That's like a little window size. So those are n-grams, like cat plus the words around it would be one. The plus the words around it is another n-gram. So we're gonna build n-grams out of all of our data. And then we're gonna train up a skipgram model, that neural net that we went through. And then after we've got our neural net trained, this is where the cool stuff happens. We need to vectorize our examples. So that neural net that we lopped off the last layer, we can send in some examples and it will spit out semantic vectors. Those are the ones we can do a search with, an item similarity search. So remember how we're talking about how like Amazon has 100 million or whatever different items, and Spotify's got so many songs it needs to search through to find similar ones. We need a way to do this similarity searching really fast. And I didn't actually talk about this in the talk because I didn't think we had time. But something you can look up if you're interested is nearest neighbors or approximate nearest neighbors. And that fits right here in this index the vectors box. That's a way to like search through a billion different examples of humans in a fraction of a second. Normally, if we compare every single human with every other human, this would take too long. Like, it's not going to be a good customer experience. So we have to do it efficiently. And approximate nearest neighbor is really cool. So check it out if you're interested. But anyways, we've got our vectorized examples, and then we index them so we can search through it quickly. And then we have to save our skipgram model. I'll tell you why in a sec. We save the skipgram model and we save that index that we built. You can just throw these into like an S3 bucket or something to use later on. So that's like the training offline portion of this. The next piece that we got is where a customer is going to feel it. So customer jumps onto my website, and my website has the skipgram model loaded, and it's got the index loaded. So the customer types in soft, fluffy, cushiony beanbag, and now my model can vectorize that person's request. That skipgram model that we built that has like all the nuance and context and meaningful dimensions that we were shooting for, my model can make a vector out of that person's request. So cool, I got a vector that lives in my space, and I can search in the index really fast for similar things. I say, here, index, here's a vector that my customer just gave me. Now give me 10 back. So those 10 vectors are other pieces of furniture that are the same. So that's just kind of how that all works out at high view on the systems. And this is pretty much pseudocode, but it would almost run. And we're at 45 minutes, and I wanted to leave time for questions, but we can get through this stuff because it's pretty simple. So this would be my data prep step out in that asynchronous monthly job. All I do is like on line 9, I go out and get all my descriptions from like Postgres or whatever data source that you're using. You know, I select all my descriptions from furniture items or whatever. And then on line 11, we have a nice package. NLTK will, they've got nice functions and stuff that can help remove stop words and things like that. So we load up all the stop words on line 11, then we loop through each description. And remember, we got to tokenize, and we got to normalize, and we got to noise reduce. So we're doing that in this loop here. So for each description, we break it into sentences. And then for each sentence, we break it into words on line 16. And now we have a bunch, we have like a word array, a word list. And the next thing we want to do is filter out all the stop words, like on line 17. So now we have a cleaned up, normalized list, and we just append that to an overarching, overall list, and then write that out to a file. So what we want to do to build the skipgram, here's a super easy way. Instead of dealing with all that neural net craziness, you can use FastText. It's a pretty cool package by Facebook, and basically you just throw your data at it. Now, I'm not saying this will give you the best results in the entire world, but it's going to train a neural net for you and lop off that last layer. And so then you can call the get word vector function, like on line 6. And this could have been like where I took in my customer's query and I just vectorize it. So now that I've tested my model on line 6 and see that it can spit out a vector, I just go ahead and save it off, like into the bucket or whatever, wherever you want to save the thing. And now we got to build a nearest neighbors index. This is the piece that we breezed through, so I won't spend a ton of time here. But basically, what we want to do is we're going to use our model that we just built in the last slide, and we're going to vectorize all of our descriptions, and then we're going to index them, kind of like putting things into a database, how a database is faster at looking things up than if you try and open a flat file. We're just going to enter all these vectors into our index, and then we save that index out, you know, to the bucket or whatever you're doing. And then here's the bread and butter where it all ties together. This is a Flask app. And we've got one route, like mycoolwebsite.com/search. And that's where I take in your query, like on line 20. So I grab the query from the user, and then I run pre-processing. So I need to normalize and strip out stop words and stuff from the user's query. And then, like on line 24, I just build vectors from my model that I loaded up higher on line 7. I just grabbed that model that we saved out to a bucket and loaded it up. So now I build vectors, and now I can use my index. Like on line 27, I say index.search. Here's the vector that we just built from my user's query. And the FICE index will send back some skews and distances, and then I can send them to the customer. So yeah, that's all we got. Hopefully there's questions.
And reminder, please submit questions either in the Slack room 2 or in Slido, either or. Nothing yet has come in, Adam, but let's give it a minute.
Okay. Maybe everybody fell asleep. I probably would.
I don't think so. Okay, got one from Danny Warren. Seems like the primary use case of this is search, question mark.
Not necessarily. I guess it depends on how you think of it. So, okay, so like what about when earlier on I was talking about in the medical field, they can use this for genetic defects and successful treatments for them. In a way, I am searching for similar defects so that I can match those up to their successful treatments. These are ones we already know about. And then I've found a new genetic defect that's like these. So I am searching for similarity, but how you use it doesn't have to be search. You can use it to suggest things to people, like in retail, when they have those, you click on, you know, you're buying a bike seat. So you click on a bike seat, and then down below your bike seat's description, there's like 10 other items. And you got bike seats and tool packs and stuff. They're all kind of bike related and similar. So you can suggest things to people. You don't just have to use it for searching. And like, it really is, there are broad applications. You just kind of have to think of it like a human. Like, this is how I solve a problem. It's a similar solution to that solution set, which is a similar problem set, you know, so I can apply my solution and it should work. Hopefully that made sense. Like, you don't need to use it just for search, but yeah, it works in search.
Danny said that makes sense.
Awesome, cool.
Just give it one more minute.
Yeah, I can wait.
Awesome. Okay, one more question, Adam, from Mike Lazzoni. In this retail example, there is imagery and description text. We use the description text for training, but could you combine image recognition and pass the images, into the training as well?
Yeah, that's an awesome question. So we've been experimenting where I work with trying to combine vectors like that. So let me back up a little bit. When you build an image vector, it's going to be trained, the embedding space for images is other images and their dimensions, which is different than my text embedding space. So the tricky part is, how would you combine two universes with totally different dimensions? I haven't found a way to do it seamlessly, but you can use both of them. So you would create a different embedding space for your images and have a process that can similarity search in images, and you can have a similarity search in descriptions. And there are techniques where you can combine at that level, but you can augment searches, right? So like you can say, well, here's 10 that the image search said was good, and here's 10 that the description search said was good. We have 4 overlapping, whoops, I need to count. We have 4 overlapping responses. Maybe these are good similarity search, even better than the 10 or 10 when we just did it alone. But that's a tricky problem. It's a cool question.
Awesome. Mike said, yeah, totally makes sense. Thank you.
Yeah, very welcome.
Okay, one more question, Adam, from Mike. Have you tried GPT-3, Adam?
I don't believe I have. If I did, I don't remember. But I don't think I have. What's GTP3?
GPT-3.
GPT-3. Well, I guess I can just DuckDuckGo that.
Yeah, Slack message maybe?
Yeah.
I can have Mike Slack message you directly.
Cool.
Cool. All right, Adam, I know we are at 4:29, so Adam, any closing remarks? And happy to end it there if we need to.
Cool. No, I'm good. Thanks everybody for watching.
Thanks, everyone. Great questions. Thanks a lot, Adam. Great presentation.
Yeah, great questions. Thanks, guys. We'll see you.